we are discussing propagation of light inside the optical fiber. In the beginning, we took the light in the form of rays and investigated the propagation of light inside the optical fiber by using phenomena what is called total internal reflection. Then we found the limitations of that model, and then we started investigating the advanced model, what is called the wave model, for propagation of light inside the optical fiber. So, for wave model, essentially we defined first the appropriate coordinate system for the optical fiber, which is the cylindrical coordinate system. So, we assume that the core of the optical fiber is a solid glass rod having a refractive index N1, and then we assume that the cladding is of infinite size with a refractive index N2. So, essentially we are solving the wave equation for this structure which has only one interface between the core and the cladding. Then by using the physical understanding which we developed from the ray model, we tried to solve the wave equation, and then we found that the radial variation of the electric or magnetic field is given by the Bessel functions inside the core, and it is given by the modified Bessel function inside the cladding. So, the phenomena essentially which we utilized for establishing this was that inside the core we have a interference phenomena, and because of that we expect that the field variation would go through maxima minima, whereas if you go inside the cladding, then the field should die down monotonically as we go away from the core cladding boundary, and that variation was appropriately given by the modified Bessel function k, whereas the variation which was of oscillatory in nature, that was given either by the Bessel function or by the Neumann function. However, we found that for the Neumann function, if r equal to 0 point is included, then the field would go to infinity, and because of that the Neumann function would not appropriately represent the field variation inside the core. So, with this understanding, essentially we got the expressions for the longitudinal component of the electric and magnetic field inside the core, which is given as A j nu u r e to the power j nu phi minus j beta z plus j omega t. Similarly, the magnetic field also is given by some other arbitrary constant B, and the same variation, the j nu u r e to the power j nu phi minus j beta z plus j omega t. This quantity u, what we can call as the radial propagation constant inside the core, is given by the square root of beta 1 square minus beta square, where this beta is the phase constant of the mode or the field distribution which is going to propagate inside the fiber, and beta 1 is the phase constant of the medium which is filling the core, that is the refractive index N1. So, if you assume that you have an infinite medium of refractive index N1, and if you ask what would be the phase constant of a wave in that medium, that essentially would be equal to beta 1, and that is essentially given by this. So, beta 1 square is beta naught square multiplied by N1 square, and beta naught square is the phase constant of a wave in vacuum. Inside the cladding, we had the field variation which was given by modified Bessel function. So, we had this arbitrary constant c, and then we have this k which is the modified Bessel function of order nu, and then we have this argument which is wr, where w is given by beta square minus beta 2 square, where beta 2 is the phase constant intrinsic to the medium of refractive index N2. And we saw that these quantity u and w both have to be real for appropriate representation of the field. So, if u becomes imaginary, then the j function will not remain oscillatory function. In fact, it will become modified Bessel function. Similarly, if the w becomes imaginary, then the modified Bessel function will become normal Bessel function and they will not represent appropriately the fields. So what we find is that once we have chosen this functional form for the fields inside the core and cladding, we have essentially put the condition on beta in an indirect fashion, that is, beta has to lie between the two bounds which are given by beta 2 and beta 1. So the lowest value of beta is equal to beta 2, which is nothing but beta 0 into n2, and the highest value of beta is beta 0 into n1. So now if I get the phase constant beta, and if I divide this quantity beta by the free space phase constant, which is beta naught, we get a number which would lie between n1 and n2. So essentially we can say that if I define this quantity beta divided by beta naught as something what is called the effective refractive index of the modal propagation, so let us say this is n effective, then the n effective would lie between n1 and n2. So you have this quantity n effective, its lowest value will be n2 and its highest value will be n1. So either we can talk the propagation characteristic in terms of the phase constant beta, or we can talk in terms of what is called the effective modal index, what is called n effective, which gives you the velocity of a wave on that structure. So we will later understand the physical meaning of why you have these two bounds here, n2 and n1. But let us complete our analysis of the wave equation. So once you have got the longitudinal component of electric and magnetic fields, then as we have seen earlier, we can use the expressions for transverse fields in terms of longitudinal components, and we can get the total electric and magnetic field inside core and cladding. So essentially now we have got 6 components: ER, E phi, Ez, HR, H phi, Hz, and suffix 1 denotes these quantities inside the core. Similarly, you have ER, E phi, Ez, HR, H phi, Hz with suffix 2. These quantities represent inside the cladding. Once you get these 6 components, then we can apply appropriately the boundary conditions at the core cladding interface, that is at R equal to A. So we have a boundary conditions now at R equal to A, which is the core cladding interface. And from our basics of electromagnetics, we know that there are 4 boundary conditions which you can impose. We can apply the continuity of the tangential component of electric field. We can apply the continuity of normal component of magnetic field, and so on. However, in this case, since we are talking about the media which are purely dielectric media, there are no surface currents, where the conductivity for the cladding and the core is 0. In that situation, not only the electric field tangential component is continuous across the boundary, but even the tangential component of magnetic field is continuous across the boundary, because the surface currents are 0. So we essentially apply 2 boundary conditions here. So we say tangential component of electric field is continuous at the core cladding interface, and then we say tangential component of magnetic field is continuous since there are no surface currents. So now if I go to my geometry here, the cylindrical geometry, you will see that the 2 components are tangential to this interface. Now here when I am saying the interface essentially is defined by this cylindrical surface. So any field which is along the z direction is tangential to this cylindrical surface. That means the z component of either electric field or magnetic field is tangential to the interface between core and the cladding. Similarly, if I consider a field which is phi oriented, that will be tangential again to this interface. So when I apply the boundary conditions, essentially we have these four quantities here, that the phi component of the electric field is continuous, z component of electric field is continuous, phi component of magnetic field is continuous, and z component of magnetic field is continuous. So we get here E phi 1 equal to E phi 2, Ez 1 equal to Ez 2, H phi 1 equal to H phi 2, and Sz 1 equal to Sz 2. So once I get the expression for the longitudinal components and the transverse component, by equating this, essentially I have got four equations now. And how many unknowns we have? We have 5 unknowns overall. We have 4 arbitrary constants A, B, C and D, which are representing the magnitude of the electric and magnetic fields, and the component beta, which is the phase constant of that field distribution in the fiber. So overall we have 5 unknowns, and from the boundary conditions we get 4 equations. So essentially what we can do is we can eliminate these quantities A, B, C, D from these 4 equations, and then what we get is the characteristic equation of the modal propagation in the optical fiber. So if I equate the tangential components and eliminate this arbitrary constant A, B, C, D, then we get the characteristic equation of a mode, which essentially is given by this. Here you have this quantity here J nu prime UA and K nu prime UA, where the prime denotes the derivative of the Bessel function or modified Bessel function with respect to argument. So essentially the J nu prime x is d by dx of J nu x, and similarly K nu prime x, that is d by dx of K nu x. So just for the simplicity, we write down the characteristic equation in this form. So you have here a derivative of Bessel function, you have a derivative here for the modified Bessel function, and this equation essentially now represents the characteristic equation for a general mode which is having all 6 components. Because we have taken all the 6 components, started with the 2 longitudinal components Ez and Sz and all these 4 components which are transverse. We got a characteristic equation now which is in general true for any arbitrary field distribution with 6 components. So this mode, as we saw earlier, that if all the 6 components are present, then we designate this mode as the hybrid mode. So this is nothing but the characteristic equation for the hybrid mode. The quantities u and w, as we defined earlier, the u square is omega square mu epsilon 1 minus beta square, and w square is equal to beta square minus omega square mu epsilon 2. Now if I consider the special case of this equation, that is for nu equal to 0. And what is nu representing here? The nu represents the variation of the field in the azimuthal direction or in the phi direction, because we have the functional form for this field which is e to the power j nu phi. So we get a variation of electric or magnetic field in the phi direction, which is given by e to the power j nu phi. So if I take nu equal to 0, then that represents a circularly symmetric field, or a field which does not have a variation in the azimuth direction. So if I look at the function which is e to the power j nu phi, the nu equal to 0 gives me circularly symmetric field. And if nu is not equal to 0, then we do not get circularly symmetric field. It will have a variation in the phi direction. For example, if I take nu equal to 1, then I will have one cycle variation as I move in the direction of phi. If I take nu equal to 2, I will have two cycle variation in the azimuth and so on. So, for nu equal to 1, if I consider the fiber like this, it will have a one cycle variation in the azimuth. That means this will be, let us say, start with 0 here. It will be maximum in this direction. It will go to 0 here again, and it will go to minus maximum in this direction. So, as I move along this in the phi direction, the field will see a variation going from 0 to maximum to 0 to negative maximum. Similarly, if I take nu equal to 2, then I will get the variation which will be going into two cycles now. So, it will be something like this. This will be 0 going through positive maximum, will be 0, will be negative maximum, will be 0, will be positive maximum, 0 and negative maximum. So, this quantity, the index nu, essentially is telling us how the field amplitude is going to vary in the azimuthal direction for a given value of r and given value of z. One thing you immediately note here is that if I consider no variation, which is this circularly symmetric case, then the field will have a maximum at the center of the fiber. Whereas, if I consider any value of nu which is not equal to 0, then on this side of this line you have the value which is positive, and on the other side you have a value which is negative. You should have a continuity of the fields from this part to this part. So, essentially the field must be identically 0 at the center of the fiber. So, if I take nu equal to 0, then we get circularly symmetric fields, and these fields would have a maximum intensity at the axis of the fiber. Whereas, if you take nu equal to 1 or nu equal to 2 or any other value of nu, then essentially the field must go to 0 at the center of the fiber. Now, if you recall the discussion in the ray model, we had two types of rays. One was the meridional ray, another was the skew ray. And the property of meridional ray was that all the rays start, they again come and join the axis. So, you have a constructive interference of the rays at the axis of the fiber. So, you have a intensity maximum at the axis of the fiber. Whereas, if you go to the skew rays, then we saw that the skew ray always spirals around the axis of the fiber, and because of that you have low intensity at the axis of the fiber. Precisely, that is what these two quantities are telling us, that if I consider a circularly symmetric case which corresponds to nu equal to 0, then these modes or these field essentially correspond to the meridional rays. Whereas, if you take any other field distribution or modes which correspond to nu equal to 1 or higher values, then they correspond to the skew rays. So, these are all 1, these are the skew rays. Whereas, this one is the meridional ray. So, you can see one-to-one correspondence between the ray model and the wave model, and that is always good, because whatever understanding we have developed from the ray model, that should support the more deeper understanding what we are going to develop from the wave model. So, now this set of rays which correspond to nu equal to 0, These are circularly symmetric and these are special rays. So that is the reason we want to find out what would be the characteristic equation for nu equal to 0, because they are the one which are going to represent the meridional rays. So if I put nu equal to 0, essentially the equation, the right hand side of the characteristic equation goes to 0, because here nu is appearing here. So this quantity is 0, and then we get the characteristic equation essentially reduced to this. Since the product of these two terms equal to 0, we may have two solutions, either this bracket going to 0 or this bracket going to 0. So what we find here is that if I had taken a transverse electric case or transverse magnetic case and gone through the whole exercise of matching boundary conditions and so on, this bracket equal to 0 would come as the characteristic equation for the transverse electric mode, whereas this bracket equal to 0 will come as the characteristic equation for the transverse magnetic mode. So this bracket here essentially is representing the TE mode, and this bracket here equal to 0 is representing the characteristic equation for the transverse magnetic mode. So if I take this bracket and equate it to 0, this will be the characteristic equation for the transverse electric mode. And what we can do is we can use the recurrence relation for finding out the derivative of J function. So the J0 prime x is nothing but minus J1 x, and same is true for the K also. So if I substitute now into this, we get the characteristic equation for the transverse electric mode, which is given by this. An important thing is that the transverse electric mode is always going to be circularly symmetric. Similarly, if I take this bracket and equate it to 0, we get the characteristic equation for the transverse magnetic mode. So we have a very important conclusion, and same thing we had seen for the ray model also, that a transverse electric mode and a transverse magnetic mode have field distributions which are circularly symmetric. Whereas if you take a hybrid mode, the hybrid mode has a field distribution which is essentially circularly non-symmetric, because that corresponds to the nu equal to 1, nu equal to 2 and so on. So by this now then one can write down the field distributions for various modes. So if I now take this characteristic equation here and I solve this characteristic equation, immediately it will be clear that this equation has multiple solutions. And why multiple solutions? Because J1 and J0, both these functions are oscillatory functions. So they cross 0, they become negative and so on. So essentially, depending upon the value of A, you will get multiple solutions to this problem. So for a given size of the optical fiber, one has multiple solutions to the problem. So now I have, for designating a mode, I have two quantities now. One is, what is this azimuthal index nu, which tells how many cycle variation the field has in the azimuthal direction. And second, which solution of the equation is representing the mode. So if I get the first solution, then I have a combination of some nu and the first solution. If I take second solution, then I have a combination of nu and second solution and so on. So in general, then we can designate a mode which is TE, and for TE, since the nu is always equal to 0, is first index we put as 0, and then depending upon the solution, whether it is the first solution or second solution or third solution, we put some index m. So we get the modes for the transverse electric, which could be TE01 mode or TE02 mode and so on. The same argument is true for the transverse magnetic case also. So, we have a transverse magnetic case. Again, the nu is 0 for transverse magnetic case. So, this index is 0. And then depending upon which solution we have, you get index m. So, you can get a mode which could be transverse magnetic 0 1 or transverse magnetic 0 2 and so on. Similarly, if we take a general mode which is given by this characteristic equation, then we know for this one now the nu essentially has to be non-zero, and then we can designate this hybrid mode by HE mode. So, we get a mode which is HE, and here the index is nu which is not equal to 0, and the solution which could be the first solution or second solution or third solution. So, now inside the optical fiber we have three sets of mode which are propagating. The transverse electric mode with the first index 0, and first index here gives number of cycles in the azimuthal direction, and second index tells the solution number of the characteristic equation. Also, this quantity essentially tells us how many maximas we have in the function in the radial direction. So, if I consider the first solution, then you have only one maximum which is at the center. If I take m equal to 2, then 1 0 would have crossed in the Bessel function and so on. So, now these two indices which we have for each of the mode, either TE or TM or hybrid, which is HE. The first index tells the variation of the field amplitude in the azimuthal direction or in the phi direction, and this one, second one, index, tells us how many zero crossings you have in the radial direction. So, zero crossings are this quantity minus 1. So, if m equal to 1, there is no zero crossing in radial direction. If m equal to 2, there will be 1 zero crossing in radial direction and so on. So, if I say that I have a TE 0 1 mode, then this mode is circularly symmetric and it does not say with zero crossing in the radial direction. So, if I take this and try to draw the fields for this, it is circularly symmetric. So, if I draw the field distribution in this as a function of radial direction, the field distribution would go something like this. No zero crossing is reached till the end, and then the field decays exponentially in the cladding. Whereas, if I consider a mode which is, let us say, T02 mode, then the field variation is circularly symmetric. It does not have any variation in the phi direction, but one zero crossing is there in the radial direction. So, if I look at the field for this, the field would be, it will be maximum at the center, somewhere it will cross through 0 till you reach to this point. One zero crossing has taken place, and then the field exponentially decays as I go inside the cladding. So, the field distribution would look something like this. Or if I look at the intensity pattern of this mode, then this will show me intensity maximum at the center, and then the intensity will slowly reduce toward the core cladding boundary, and it will keep reducing as I go inside the cladding. So, if I draw here the intensity variation, I will get a very bright spot here at the center, and then slowly the intensity will reduce as I go away from this, and then it will simply merge with the intensity in the cladding. Whereas, if I take the intensity distribution in this case, Then it has a very bright spot at the center, which corresponds to this. Then the field intensity reduces, it becomes 0 at this, and here the field becomes negative. That means the field direction reverses. So you will get a very bright spot here. It will reduce slowly here, go to 0, and then it will become a negative field here, heading like this. So you will get a bright region at the center, then there will be a dark ring somewhere in between, and again you will see a bright ring of light with a electric field orientation opposite to what you are having at the center, because the function has become negative. So like that we can visualize now the field distribution inside the optical fiber by the nomenclature which you have defined, that the first index tells us the variation of the field amplitude in the azimuth direction, and second index -1 tells us the number of zero crossings in the radial direction. With this understanding, then now one can go and look at some more features of this, and that is, now if I look at this quantity u square which you have defined here, which is u square is equal to omega square mu epsilon 1 beta 2, and w square is equal to beta square minus omega square mu epsilon 2. You find that sum of these two quantities is independent of beta. So u square plus w square, if I take, that is nothing but omega square mu epsilon 1 minus omega square mu epsilon 2, and this quantity, as we know, is beta 1 square. So this is beta 1 square minus beta 2 square. So for a fiber of radius a, now we can define a quantity which is a square multiplied by this one, which is a square multiplied by beta 1 square minus beta 2 square. And if I write down explicitly beta 1 and beta 2 as beta 0 square into n1 square minus beta 0 square into n2 square, we get this parameter which is a characteristic parameter for the optical fiber. Why it is a characteristic parameter? Because there are only three quantities involved in defining this optical fiber: the refractive index of core, the refractive index of cladding, and the radius or the diameter of the optical fiber core. So you recall that the parameter which we had defined, the numerical aperture, that was a characteristic parameter for optical fiber, but the size of the core was not coming into picture while defining numerical aperture. The numerical aperture is purely defined in terms of the refractive indices of core and cladding. But we have seen that just the difference in refractive index does not completely characterize the fiber propagation, because depending upon the size of the core, the different modes or different numbers of modes can propagate in the fiber. That means just a parameter which is defined on the basis of refractive indices doesn't completely describe the propagation characteristics. So now we find here this parameter is a more complete parameter for describing the fiber. And if I simplify this quantity V will be equal to A, you can take beta common from here. So A into beta 0, the square root of n1 square minus n2 square. And as you know, beta 0 is the free space propagation constant, which is given by omega upon c, where c is the velocity of light in vacuum. You get this quantity V, which is A omega upon c square root of n1 square minus n2 square. So if I write this quantity, realizing that this quantity we already know, which is nothing but the numerical aperture of the optical fiber, we can define this characteristic parameter for the optical fiber, which is what is called the V number of the optical fiber. So, V number is a more comprehensive parameter for the optical fiber because it has its radius included in this, it also has the numerical aperture included in this, and radius is normalized with respect to the wavelength. Because if I write down this quantity here, C omega is 2 pi into frequency, C upon frequency will be lambda. So, you get a V number which essentially is given by this. Now, this V for a given parameter, since N1 and N2 is constant, the radius is constant, the V number of an optical fiber is directly proportional to the frequency omega. That is the reason many times this parameter is also referred to as the normalized frequency. And later on we will see this is the parameter which is essentially used to compare different types of fibers. So, this parameter V number of an optical fiber is one of the extremely important parameters because that is the one which is going to describe the propagational characteristics inside the optical fiber. Now, before we make use of this parameter, the V number, let us come back to our understanding that your beta had two bounds which were given by your beta 2 and beta 1. And you have this relationship between U and W which is essentially given by this. So, now if I look at this quantity here W, and W times R is the argument of the modified Bessel function. If W becomes 0 or if this W becomes imaginary, then the modified Bessel function does not remain modified Bessel function. That is what we saw earlier. That means, if this quantity W becomes imaginary, then the field variation will not be appropriately described like a exponentially decaying fields in the cladding, and we will say that this mode is no more remain a guided mode. The energy will start leaking inside the cladding. Since we want that there has to be sustained propagation energy only along the axis of the optical fiber, the field must die down monotonically in the cladding. Or in other words, as we saw that this quantity beta has to be greater than this quantity. So, when beta approaches this quantity or when beta becomes equal to this quantity or beta becomes equal to beta 2, that time your modified Bessel function gets converted into the normal Bessel function, and then there is no confinement of the energy inside the core because the field does not die down monotonically in the cladding. So, we define this condition as what is called the cutoff condition for a mode. So, we define a condition what is called a cutoff condition when beta tends to beta 2. What does this physically tell me now? That if let us say beta is equal to beta 2, suppose, what that means is that whatever energy is propagating inside this medium, it sees basically a refractive index N2. That is the reason it has a propagation constant which is beta 2. Or in other words, it is telling us that most of the energy associated with these fields is lying in a medium which is having refractive index N2. That means most of the energy is lying inside the cladding. So, as beta approaches beta 2, more and more energy is spreaded inside the cladding. Similarly, if I have a situation where beta approaches beta 1, then more and more energy is confined inside the core because most of the energy sees the refractive index which is equal to N1. Now, we can understand this physical picture very easily. that why beta lies between these two limits, beta 1 and beta 2. Because for an optical fiber, part of the energy is lying inside the core, part of the energy is lying inside the cladding. If you had left to themselves, the fields which are lying inside the cladding would travel with a phase constant which is beta 2. The field which are lying inside the core would travel with a phase constant which is equal to beta 1. But now these fields are tied together by this mode, by the boundary conditions. So the field inside the cladding and core, they cannot move with arbitrary phase constants the way they like, but they have to come to an agreement that the phase constant for the fields in the cladding has to increase a little bit, for the fields which are inside the core have to reduce a little bit, so that they can travel together with the same phase constant beta. So essentially the limit of beta 2 and beta 1 is telling us that the energy is there in these two regions, and because the energy which is outside the core has a tendency to travel with phase constant beta 2 and energy in the core has a tendency to travel with a phase constant beta 1, there has to be a mutual agreement so that they can travel with a phase constant which lies between these two limits. But this also tells you something more. What this tells is that if I look at the behavior of beta, if beta is very close to beta 2, then most of the energy lies inside the cladding. So without even worrying or without even finding out how the total fields are distributed and so on, if I can get this parameter beta, and if this beta lies close to beta 2, we can immediately say that most of the energy is lying inside the cladding compared to inside the core. If we can get a situation where beta lies very close to beta 1, then immediately we can conclude that most of the energy is lying inside the core and very little energy is lying inside the cladding. So as beta goes towards beta 1, the energy gets more and more confined inside the core and very little energy remains inside the cladding. And that's a very desirable feature. That's what we want in the propagation of light, because if the light has to be free from interference from the external world, the light should be very well confined inside the core. So we have to create a situation, we have to operate in a domain where beta should be as close to beta 1 as possible and away from beta 2 as possible. So this condition, what is called the cutoff condition, at which the mode propagation essentially ceases, or the mode starts now leaking out inside the cladding. Beyond that, the mode propagation doesn't remain any meaningful, because we very quickly lose the energy inside the cladding. So for a good well confined propagation of light inside the core, we should make beta as large compared to beta 2 and as close to beta 1 as possible. Now with this then, one can say that if I now look at the variation of beta as a function of frequency, because that's what our interest was, let me recall, we started this analysis to understand how the beta is related to omega. Because once we get this relationship between beta and omega, then we can find out the phase velocity, which is omega by beta. We can find out the group velocity, which is d omega by d beta. So the whole exercise was essentially to find out the relationship between the phase constant beta and frequency omega. And what we have found here is that this V number now is related to the quantity which is the frequency, it is proportional to frequency. So except the proportionality constants for a given fiber, we can use for omega the V number V. Similarly for beta, what we can do is we can define a parameter, what is called the normalized propagation constant, which can be defined like this. Now, we have seen earlier that this quantity, the effective refractive index which we got, it has a limit which goes between N1 and N2. So, when the mode approaches cutoff, the N effective essentially approaches N2, and when the mode is far from cutoff, then N effective will approach N1. Most of the energy will get confined inside the core. So, instead of plotting now beta as a function of frequency, we can get a plot of beta with respect to V, because V is proportional to omega, or we can have a normalized plot of this quantity which we call as B, which is defined as N effective square minus N2 square upon N1 square minus N2 square. And this will lie always between 0 and 1, because at the cutoff N effective will tend to N2, so this quantity will go to 0. When we go very far from cutoff, N effective will tend to N1, and that time this quantity will become equal to 1. And that is the reason we can call this quantity as the normalized propagation constant. So, beta will vary from beta 2 to beta 1, but this normalized propagation constant will always vary between 0 and 1, irrespective of what mode we are talking about. So, whether we have a TE mode or we have a TM mode or we have a hybrid mode or whatever the index is, the limits for this is always between 0 to 1, or limit for beta is always between beta 2 and beta 1. So, now instead of having a plot or variation of propagation constant beta as a function of frequency, we can get a variation of this normalized propagation constant as a function of V number, because V number is proportional to frequency and this quantity essentially is quantity beta. So, here we have plotted here the quantity beta divided by beta naught, which is nothing but your N effective. As we have seen, N effective will range between N2 and N1. For a particular mode, we can vary the V number and ask how the beta varies. So, essentially the characteristic equation which we have got, you have to solve that characteristic equation numerically, get the value of beta for various values for V numbers, and note here the size or the refractive index of core or cladding, the individual don't matter. What matters is the total together, what is called the V number. So, we can have this quantity V number, which is a representation of frequency on this axis, and on this axis we have the normalized propagation constant B, which will vary between 0 and 1, or a effective refractive index which is going to vary between N2 and N1. So, what we find is that as the V number increases, all these graphs are monotonically increasing graphs. This is the graph which corresponds to HE11. Then we have the graphs here which are T01, TM01 and HE21 and so on. So, first thing to note here is that this quantity V, which is proportional to frequency, there is only one mode which can propagate down to V equal to 0. Though the value is here very small, essentially this curve can extend up to 0. So, no matter how small the value of frequency is, this mode, HE11 mode, is the one which is always going to propagate on the optical fiber. Whereas, if I consider a mode TE01 mode, which is the first mode in transverse electric, or TM01 mode, then the V number has to be greater than certain value, and this quantity here is 2.4. What is special about 2.4? 2.4 is the first root of J0 Bessel function. So, the cutoff for the T or Tm is given by the roots of J0 Bessel functions. So, the first 0, since it is 2.4, you see that for T or TM mode to propagate, the V number has to be greater than certain value. Or for a given fiber, the frequency has to be above certain value. If it is not above certain value, then the T and TM mode will not propagate. Whereas this mode, which is the HE11 mode, this will always propagate because its cutoff frequency is 0. So we find something very interesting, that between the range between V number 0 and 2.4, only one mode propagates, okay, and that mode is not transverse electric or transverse magnetic, that mode is a hybrid mode. So it is very interesting that the mode which is predominantly propagating on the optical fiber has in general all 6 components associated with it. It is neither transverse electric nor transverse magnetic. If I compare this with the metallic waveguides, then in metallic waveguide the dominant modes are transverse electric modes. Whereas if I go to the dielectric waveguide like optical fiber, then the dominant mode is not transverse electric, but the dominant mode is hybrid. So now if I check this back with my ray model, essentially what that tells me is that this mode which is going to propagate here between this and this V number, that must correspond to the ray which was going along the axis of the optical fiber. Because all other rays had to satisfy certain phase condition for total internal reflection. Only the ray which was going along the axis of the optical fiber was independent of all these quantities. So even if I take the size of the optical fiber very small, one ray which goes along the axis of the optical fiber will always go. So this mode, HE11 mode, is the mode which corresponds to the ray which travels along the axis of the optical fiber. So it is a very important conclusion that the ray which goes along the axis of the optical fiber, if I had seen only in terms of ray, it would look as if it is a transverse electromagnetic light which is going to propagate. So from the wave analysis, we find that that ray is not transverse electromagnetic in nature. This wave is hybrid in nature. So now we got a very important conclusion, and that is we have got essentially a analytical answer to the range of parameters or the frequency over which only one mode will propagate inside the optical fiber, or the condition for which the fiber will be single mode optical fiber. Recall, we had said when the large number of rays propagate, there is going to be more broadening of the signal, what is dispersion. Whereas on single mode, there was no dispersion because of the multiple ray propagation. So we wanted to know what is the quantitative measure which tells us whether the fiber is going to be single mode or whether the fiber is going to be multimode. And here is the quantitative answer, that if the V number of the optical fiber is less than 2.4, then the fiber will be single mode. If the V number of the optical fiber is greater than 2.4, then the fiber will be multimode. And as the V number increases higher and higher, more and more mode starts propagating inside the optical fiber. So in conclusion, essentially our analysis which we have carried out has given us a very important information about the quantitative parameter of the fiber, what is called the V number, that if the V number is less than 2.4, then the fiber remains a single mode optical fiber.